Hello, my name is Kyle, and in this video you will learn all about how chemistry is applied in the production and function of pharmaceuticals. Yay! Now first off we have collision theory. And yes, the background to this slide is actually just a picture of two planets colliding, which isn't really collision theory, but I thought it's somewhat fitting since collisions and their magnitude are the main idea of this topic. Now on to the first real slide. So Kyle, what exactly is this collision theory you keep going on about? Well, collision theory essentially describes the criteria that must be met before a reaction can proceed. When describing this theory, the two factors that must be considered are kinetic energy and orientation. There are also a few variables that can alter either the kinetic energy or the energy required, which will in turn determine whether or not a reaction will occur. Now the amount of energy needed for the reaction to occur is called the activation energy. Now let's take a look at this diagram. Now here the first row describes a collision that is oriented correctly but has too little kinetic energy. As you can see, there is no reaction. Now the second row has particles that have enough energy but are not oriented correctly. So again, no reaction occurs. Now the third row has both sufficient energy and the correct orientation, and as a result, a chemical reaction occurs. So next, we will have an example of how collision theory is applied in pharmaceuticals. Here we have a drug called Benadryl. Looking at the box, you can probably tell what it's used for. It's usually taken for quick relief of allergy symptoms like itching or sneezing. This is a pretty good example because this drug exists in both liquid and solid form. The liquid Benadryl has particles that move more freely than the solid version, and they have more kinetic energy, which means that a greater percentage of the particles will overcome the activation energy. And that means that a reaction can proceed. The solid pills, however, have less kinetic energy, and there is also less surface area exposed, which means that less particles take part in the collisions at once. This means that the reaction will be slower and the allergy relief won't be achieved as quickly as that of the liquid one. Now this drug here is called Cefprozil, even though the bottle says Cefsil. Cefprozil is the actual drug name. This drug is an antibiotic, which means that this drug kills bacteria by destroying their cell walls, which in turn makes them defenseless against the body's white blood cells. Now as you can see, there are two bottles. One has a concentration of 125 milligrams per 5 milliliters, whereas the other has a concentration of 250 milligrams per 5 milliliters. Now, do you remember how I mentioned the variables that influence the factors of collision theory? Well, the concentration is one of them because a greater concentration would mean more collisions, which means the reaction would occur at a greater rate. Relating back to the drug, we now know that the 250 milligram bottle is more potent and reacts faster. And the concentration must be taken into consideration because, for many people, especially children, too much of a particular pharmaceutical could prove fatal. An example of such a potentially fatal drug would be digoxin, which is a drug used to treat heart failure. Its therapeutic range is so limited that even ingesting something small could cause a reaction to occur out of the therapeutic range, resulting in toxic effects such as heart attacks and heart palpitations. Now the next topic is all about catalysts and reaction rates. So what is a catalyst? Well, they are substances that lower the amount of energy required for the reaction to occur. Now since we know that this activation energy needs to be overcome for a reaction to occur, we can also say that a lower activation energy would allow a greater percentage of the colliding molecules to have the ability to react. And with that said, that means that when there's a catalyst involved, the reaction will proceed faster than normal. Now this diagram is extremely simple, but it illustrates the idea that a catalyzed reaction doesn't need as much kinetic energy in order for the reaction to proceed. But what do catalysts have to do with pharmaceuticals? Well, first, we can't forget that enzymes, as well, are catalysts. And so the enzymes, like all catalysts, lower the activation energy. Now, an example of such catalyst use is in a very common pharmaceutical called lactate. You've probably heard of it before, and in fact, some of you guys may have had the experience of taking lactate. In essence, it allows you to digest lactose-rich foods without the symptoms of lactose intolerance, such as diarrhea and stomach pains. Essentially, lactate is a pharmaceutical that contains lactase enzymes, which lowers the activation energy involved to break down lactose. And again, as a result, a greater amount of particles can participate in creating a reaction, and the rate of reaction increases in the process. And here's what the reaction looks like. See, the molecule on the left is lactose. When the reaction between lactose and water is catalyzed by lactase, the once indigestible lactose can be broken down through hydrolysis to become glucose and galactose. And now onto the last pharmaceutical connection, buffer solutions. So what exactly does that graph represent? Well, it's a graph that represents an acid-base buffer system. A buffer solution resists change by keeping the pH within a certain range. These solutions consist of either a weak base and one of its salts, or a weak acid and one of its salts. Now, an example of such a buffer system would be present in a common pharmaceutical called Tums. Tums is used to treat heartburn and indigestion. It creates a buffer and neutralizes stomach acid. Now, what causes heartburn? Heartburn comes as a result of the acid flowing back into the esophagus. The reaction is shown here. The active ingredient in Tums is calcium carbonate, which is a weak base. When this reacts with the stomach acid, the weak base absorbs excess hydrogen ions from the HCl, which then finally allows pH to return to a tolerable level. And that concludes my presentation. Thanks for listening.